Hi everyone, my name is Letian Zhao. Today I'm going to talk about my project. My project topic is application of information theory to air pollution analysis. Okay, first, in this project, my research goal is use information theory to explain complex air quality system. We hope to use information theory as a tool to analyze air quality and help us understanding the complex air quality system. I will looking at the following five areas of the information theory. First, information entropy and AIS. Here, I mainly focus on what is the uniformity of the various indicator in the data set and their information retention capabilities, which indicator is more uniform, which indicator has strong reference capability for the future. I mainly use information entropy to check if the data is evenly spread out. When the entropy is high, it means there is more uncertainty and the data is more evenly distributed. And when it is low, is opposite. Then I use AIS to check the retention ability of the data, that is, prediction of the data for the future moment. When the indicators is large, it means the historical data has more reference value for future predictions. Secondly, I will looking at mutual information rents to analyze whether there are dependence between the various and the indicators in the data set. Finally, I will looking at the transfer entropy and the conditional transfer entropy to determine whether there is obvious transfer relationship between CO and C6H and whether other pollutants have impacts on the relationship between them. By calculating the transfer entropy of CO and C6H6 and the transfer entropy under conditions, it is possible to determine whether there is strong dependency in certain intervals. For the data set, I choose a public data set of air quality in the heavily polluted area in Italy. The data contains multiple indicators such as CO, C6H6 temperature, and humidity. The data cover the entire year from March 2004 to February 2005, recording every hours, which a total of 9,358 data samples. Next, I will talk about one method. Data first will be data pre-process. We first processing the missing value of the data, remove the indicator with more missing value, and finally remove the row with missing value from return indicator or ultimately returning 6,941 valid data. And next is data inspection. There is for pre-processing data. I normalize the data to between 0 and 1. I using maximum and draw distribution and treating graph to determine whether the data conform to common sense. In the bottom right charts, you can see there is not any streaming outliers. The data mostly follow normal distribution. And in the bottom left chart, we can see some fluctuation in the data, and it looks like there may be a bit repeating pattern. Looking at these two charts, we can see the data seem reasonable, so we are good to move on with future analysis. Next page, I will talk about the analysis of uniformity and the predictive capacity of information entropy and AIS in air quality indicators. The first picture on the upper left corner of region 1 shows the results of our information entropy bar charts. We mark two indicators with the highest and lowest information entropy in the red, which means that the AH indicator is more evenly distributed, while the CO indicator is more extreme. To check the statistical significance of the result, we looking at distributed charts in the top right region one. It's confirm what we saw with information entropy. The CO indicator is more concentrated, while the AH indicator is more even spread out. And for the lower left corner of region 2, we draw the bar chart of AIS to mark the highest and the lowest indicated of AIS in the red, which means that the AH indicator has a strong ability to retain information. Whereas CO indicator has a low ability to retain information. In other words, the AH indicator has a strong ability to predict future moments, while the CO indicator has a weak ability to predict future moment. To future check the statistical significance, we plot out a scatter diagram for these two indicators as a consecutive time point. In the bottom right chart of region 2, you can see the AH indicates almost straight line, so strong linear predictabilities. On the other hand, the CO indicates more spring out, meaning its linear, its prediction ability is weaker. Okay, next page I will analyze the dependency between air quality indicators through mutual information. The first figure on the left shows the rate of drawing mutual information rate heater map. We mark the most obvious dependency indicator in the right, which indicates that there is a strong dependency between C6H6 and PT08S2. The second picture on the right, we convey the mutual information rate in the distance address and use density based on clustering and with EPS of 0.815. The results net topology shows that the cluster represents a strong correlation group between CO, C6, H6, and PT08S2. This shows that the different pollutants in the air are not complete independent, but have some level of dependency on each others. Next page. Here we talk about use transfer entropy and conditional transfer entropy to analyze the relationship between pollutants such as CO and C6H6 and the impacts of other pollutants. In region 1, we have a graph showing the transfer entropy between CO and C6H6, while in region 2, we have looking at transfer entropy between CO and C6H6 under PT08.S2 conditions. The scatter plots using color represent the transfer entropy at each moment. Brighter color mean higher transfer entropy. In first image of both region 1 and region 2, we have scatter plots showing C6H6 value at one time point. Again, the next time point, here the color distribution fairly scatter mean there is no strong dependency between the two in the interval. Now, looking at the second image, both regions, we have a delayed scatter pulse for CO and C6H6. The scatter patterns looking similarly in the both cases. Again, color are evenly spread out without a clear difference. This indicates that interaction between CO and C6H6 does not change significantly under the condition of PT08.S2. Overall, this result suggests that the relationship between CO and C6H6 remains fairly stable, even when factoring in PT08.S2 conditions. Okay, next page, I will talk about discussion. In summary, here are what we found. First one, AH index is more evenly distributed and has strong information retention ability. CO has more extreme distribution and low information retention ability. Second one is C6H6 has a strong correlation with PT0 08.S2 and COC6H6 and PT08.S2 form strong correlation group. Third one will be CO and C6H6 do not show particularly strong dependence within a certain range, and the interaction between them will not change significantly under PT08.S2 conditions. For future work, we can consider introducing other analysis methods such as machine learning and deeper learning, introducing more interaction and introducing more friction and time spans to better understand air quality system and make our results more universal.